Hello Coach Reza and everybody watching this video. Um, this is assignment 4 and this is in continuation with the previous assignments in which John Hughes is studying a data set and he's trying to understand the pattern that cancer patients show with respect to uh, reaching a stage of remission or not based on certain parameters. Uh, so we have previously tried a few algorithms, a few models to help him in his analysis. So we've tried uh, linear regression, logistic regression, and a neural network model. And in this one, we will be trying to analyze the data with support vector machines and Gaussian Naive-Bayes uh, algorithm model. So just an overview of how the data looks. We have 6 independent variables: cell, smear, infill, li, blast, temp, and one dependent variable that is remis or remission. And let's go ahead and get to how we're going to solve this. Also, first let us look at our data. These are the six independent variables and the one dependent variable, and the amount of data that we have is 28, including the header. That means we have 27 records, and we will be splitting these 27 records into train and split, and train our model to work efficiently. So let's go ahead with coding SVM and Naive-Bayes. Uh, so the first step is importing the library, and that's done. So the second step is again reading the CSV file or the data set that's been given in CSV format, and just printing out the top 5 rows so we know that it is the correct data set that we have imported. And we split the data into x and y, x being the independent variables and y being the dependent variable. So what we do here is we drop the dependent variable and convert it into a numpy array and make it x, and only column with the dependent variable is converted to a numpy array and assigned to y. So now that we have x and y basically are dependent and independent variables in two different data frames, what we would go ahead and do is split the data into train and test. So for that we will be importing the train test split function from scikit-learn model selection, and here we go, we use the function this way by passing the independent variables. The dependent variable test size point 2 means 20% of our entire data will be taken for testing, and the rest, the 80% of data, will be used to train the model. And stratify equals y means the data will be sampled strategically so that there is no biasing in the data that is being used to help the model learn or train itself. Then we have to scale the data, since we know that all the machine learning models work better with smaller numbers rather than bigger ones. We will scale the data down. So this is the set of steps we use for that. We have imported standard scaler from scikit-learn preprocessing, made an object out of the class, and we use the fit transform function for getting a scaled x train variable, and the transform function to get the train x test variable, scaled x test variable. Now we go ahead with using the classes for SVM and Naive-Bayes. It's actually Gaussian. So and what we have imported here is SVC from scikit-learn SVM, Gaussian Naive-Bayes from scikit-learn Naive-Bayes, and to validate how well our models are performing, we need to use the metrics library and these functions from the metrics library: classification report and confusion matrix. So what we do here is we have a for loop using which we will be making objects from the classes according to the params we pass for each of these models. And so in the for loop, the first thing is we create objects for these, object for SVC, and we name it SVM. So this is how the result looks. So in the SVM we find that it's really surprising to see something like this, but the precision is 100%, the recall is 100% for both understanding and classifying zeros and ones, and obviously that makes the F1 score 1, 2. That means this model is a clear indicator that the model is actually showing overfitting, and overfitting means the model is in a way not analyzing the data. It's not instead it is memorizing the data. So something like this is going on with the model, like this. So the hyperplane that our model is creating right now is like this. This is 100% efficiency, but what happens is if there is new data that is fed to this model which doesn't follow this pattern particularly, this hyperplane will give wrong results, will classify things incorrectly. That means this model will be of no use. This is what overfitting is. This is curve overfitting. This is model overfitting when it comes to machine learning. And so this, although the precision, the accuracy, the recall for this model is good, it is 100%, but it is not a very good model to be used for data. And we'll see how the Naive-Bayes model performs. So we have the Naive-Bayes results too, and we see that the precision is 1 and the recall is 0.75. That makes the F1 score 0.86, which means the classification or the model here is not, it may be just fitting, or you can assume that it may be overfitting slightly, but since we have only 21 records that have trained this model, it's not a lot. Maybe with more iterations and more epochs, this model will show better results, and similarly the precision, recall, and F1 score for classifying yes is also 67%, 100%, and the F1 score hence is 0.8. This means the model could be, it is not 100% overfitting for sure, and it has scope for improvement when there is a bigger data set applied to it. Hence for John Hughes we would be suggesting that the Naive-Bayes model would be the more appropriate model to be used, since there won't be an issue like this. There won't be a classification that is very particular to the data that has been given, and if there is new data in the test which doesn't follow the pattern like this, the data is not going to fail, since it's not like this. The analysis won't be incorrect, or the classifications can be more reliable. So Mr. John Hughes should go ahead with the Naive-Bayes model, and that's about this assignment. Thank you for your time. Goodbye.